Okay, so good morning, everyone. Today's topic of talk is comparative planetology. It's a very general talk where I would like to cover introduction of different planets and I would emphasize on why it is important to do comparative planetology, why we should actually look to different planetary bodies at the same time, focusing on a specific object. So before we start, we have to understand that the current status of our solar system. As you can see here, we have our sun, then we have 8 planets, and then we have asteroid belt in between Mars and Jupiter, and Kuiper belt uh, beyond Neptune, and after that we have Oort clouds. This system is a very clean picture of our solar system, but when the solar system was formed, the situation was very much chaotic, and the result, what we see here, is actually shown here. Now, this planetary system also includes satellites. In some cases, satellites are so huge as a planet itself, in a rocky planet itself. I have just mentioned few of them here for your reference, and this includes our own satellite moon. Along with this planets, satellites, asteroid belt, and Kuiper belt, we also have dwarf planets, Pluto, and also one of them is here, Ceres. These dwarf planets actually fulfill most of the conditions of being a planet. Only what it lacks is that it has not cleared its surrounding, and that's why these are not actually included as planets. We also have comets, and but for today's topic, our main concentration is on inner planets. So if we further divide our planetary system, what we see is we can actually divide it into two. One is terrestrial, another is Jovian. So terrestrial planets, which includes Mercury, Venus, Earth, and Mars. These are small rocky bodies with core and mantle, in some cases with atmosphere. It has total of 3 satellites, so 4 planetary bodies and 3 satellites. One of them is from Earth, and 2 other are from Mars. From Mars. But if we look to Jovian planets, they are actually significantly different than terrestrial planets, which are actually much larger compared to our terrestrial planets. This is actually Jupiter and Saturn. They are gas giants, and Uranus and Neptune, they are actually ice giants. Basically, these Jovian planets do not have solid surface, and but it might have a small rocky metallic cores. The main content of these planets is hydrogen and helium, with traces of poisonous gases, water, and other complex molecules. These planets actually have more than 100 satellites, which are primarily made of ices. Some of these satellites I already showed in the first slide. And these satellites are actually very interesting objects. Some of them have been studied in detail through spacecraft missions. And what we see is that some of these satellites actually show signs of having some kind of uh, activities which may actually can be actually relate to origin of life. So basically, for us, when we are looking for comparative planetology and concentrating on terrestrial planets, actually the satellites of these Jovian planets are also very interesting. But for today's topic, I won't be covering that part. I will be mainly covering terrestrial planets, and even in terrestrial planets, I will be mainly focusing on Mars, Venus, and Mars, leaving our Earth out because of the time limit, but because this itself is a topic of next webinar. So, before we go in detail, we have to understand that what kind of evidences we have on Earth, which can actually tell us the story of our solar system evolution. So, the basic question which comes in mind is that how our solar system formed. So our understanding is that there was a molecular cloud which eventually condensed before started condensing before 4.5 billion years, and during this process we actually the outcome of this process was increasing in growth and forming planetesimals. So these planetesimals are heavy elements which with its own because this in the rotational system it gets its own gravitational force and start attracting elements, and that actually formed planetesimals, and these planetesimals accreted into planetary embryos. Embryos, and eventually these embryos by colliding and by accretion actually formed planets. So basically, if you just want to put it in one sentence, what we can say is that planets are result of bottom up formation from leftover materials in the nebular disk. So bottom up, it means that it has first its core, then it has mantle, crust, and then it attracts gases, which actually generates the envelope of gases, which actually joins this envelope of gases, which is actually the atmosphere. So so, what kind of evidences we have which can actually tell us or which can actually enhance our understanding of solar system formation? So, these are just some samples of meteorites. So, meteorites are basically rocks and metals from asteroids and other planetary bodies that survive their journey through our atmosphere and fall to ground. These are typically of size scale of centimeters, a few tens of centimeters to hundred of centimeters. These are naturally derived samples which actually preserve record of earliest solar system, because these bodies actually formed at the same time as our Earth formed. So because on Earth we do not have evidences of early formation, we rely on this kind of sources which are naturally coming to us, and these can be further divided into different types: iron, stony iron, stones, chondrites, and achondrites. These meteorites are not always small in size. Sometimes these are of few kilometers diameter. One of them, that example is this Barringer crater in Arizona. This is the largest crater on Earth with diameter of 1.5 kilometer and depth of about 170 meters. And this crater, because this site is accessible, we have a very good understanding, and we know that this crater actually formed before 50,000 years ago. So meteorites are actually the information, the natural sources which we get on Earth, which we study, and we actually get clues on formation and evolution of our solar system. So once we have these meteorites in lab, we can actually do a lot of things. We can actually study its physical properties, for example, particle shape, density, etc. We can have mineralogical properties. That is the basically the spectral studies of minerals, because each mineral form at a different temperature and pressure. It actually gives us. It gives us initial conditions when this mineral might have formed. Then we can also study chemical properties. We can understand the kind of weathering processes, regolith formation, etc. And this understanding actually helps us to plan our experiments on other terrestrial bodies. For example, in case of Mars, we have instruments on rover which actually identifies chemical elements in rocks, identifies minerals including those formed in water, and also identifies organics, the chemical building blocks of life. So this kind of lab study is actually the base of our space exploration, and therefore it's very important to have in-depth knowledge of lab-based study, to gain knowledge out of lab-based study. So basically, why to study more than one planet? Why to have comparative planetology? So as you can see in this figure, each planet, and in this planetary terrestrial inner terrestrial planet, I have also included moon. What you can see here is that each planet is different. The initial ingredients for each planet is actually same. Then why it is so that every planet is evolved in a different way? To understand this, we have to study more than one planet, and we have to go for approach of comparative planetology. In case of Earth, here I'm just showing you the structure of Earth, which is first it has inner core in solid form, then outer core in liquid form. Then we have mantle, and on top of mantle is crust. And what we can see is this ice caps, and then we have atmosphere. The crust of Earth can be actually divided into two: continental crust and oceanic crust. So basically, because we have access to our own planet, even after that we actually rely on orbiter missions. Some of the information, the global information, what we get, or what we could actually get was actually through orbiter missions. So that's why you can it's very very important to actually do comparative planetology to understand the overall solar system evolution, and the reason of why each planet has been evolved in a different way. So the basic characteristic of any planet, we as a first step, we want to know its orbit, its mass, size, rotation rate, and direction, its shape, temperature, magnetic field, surface, and atmospheric structure. So these set of information actually give us in-depth knowledge about uh, the initial conditions in which this planetary body formed. Uh, as we already discussed in previous slide, that the initial ingredients for each planet is same, but what you can see here in this figure is that there are a lot of differences. Even just if we compare inner planetary terrestrial planets, so inner planetary bodies, Mercury, Venus, Earth, Moon, and Mars, what we see that the size of Mercury is comparatively it's almost half of Earth and Venus. But if you see, density is actually similar. In case of moon, though size of this is small, it's smaller than Mercury, is comparable. But when you see its density for such a small body, actually you see that it is actually comparable to Mars. So if you compare size of Mars and Moon, Moon is almost half of the size of Mars, but when you compare density, it is actually comparable. Then some planets have atmosphere, like our Earth has nitrogen and oxygen as main major contents of atmosphere, whereas Venus has CO2 as dominant um, gas. Mars is having a very thin atmosphere, and Moon and Mercury do not have atmosphere. So, why this kind of dichotomy exists? So, these are the questions we actually want to attempt through doing comparative planetology. So, one of the major key player in planetary evolution is giant impact. So, initially, our understanding was that the formation of our planetary system was relatively a smooth process, whereas after studying different planetary bodies, now we know that the formation of our planetary system has gone dramatic shift. So basically, what happened was towards the end of planet formation, our planets actually experienced several huge collisions that actually stripped away some part of its crust, mantle, and actually molten the overall body, which again gave rise to crystallization process. Just if we take example of Earth and Moon system, this is the our Moon is considered as originated from giant impact on the prototype Earth by a Mars-sized planetary body. Another example, if we see that Uranus is actually it actually its spin axis is very different. It's about 90 degrees to the rest of the solar system, and that could also be a reason of some kind of impact. So it is obvious that giant collisions are integrated part of planetary formation processes, and this could be also a reason that this could be a reason that in why life actually flourished on our own planet. So it's very important to understand giant impacts. So this kind of chaotic situation actually was very much obvious in initial time, and there are several questions which I have listed here. So are the Moon and Earth made of same materials? Probably yes, probably not. We have to understand that part. Did giant impact strip away hydrogen helium atmosphere before the endosphere could develop? Are tilted planetary equators away from their orbital planes at different angles are a result of giant impacts? So these are still some open questions, and what we have to understand through comparative planetology. So basically, if we talk about planetary geology, it is simply a building block or a basic block of overall system. As you can see here, so this basically focuses on study of structure and composition of planets, history and processes which result in their present state, and compare results among all the planets to understand geological processes. So I hope that with these few slides I could convey you that why it is important to do comparative planetology with one specific target. We do not get the whole picture, and that's why it is important. And actually this planetary geology is connected with different branches of physics and chemistry, biology and all. So basically, to understand the overall evolution process, we have to combine all these branches, and this is just one block of the overall system. So we started space exploration with Sputnik in 1957 with the aim of fulfilling the missing chapters of formative years of history of our own planet Earth. So as I said, that some of the information of our own planet we got from orbiter missions. The synaptic view of the Earth provided by orbiting spacecraft was actually duplicated step by step for Moon, Mercury, Mars, and Venus. So first we had missions to our own planet, and the same understanding we tried to implement in other planetary bodies. And we did not just limit ourselves to orbiter missions, but that also included lander, rovers, and in case of Moon, we had human exploration that that basically helped us to understand each and every planetary body, terrestrial planetary bodies in detail. So we can say that this actually was a transit from understanding planetary bodies from astronomical objects to geological objects, because we started getting maps of surface which could actually give us much more detailed information than just having observations in form of a spot in the sky. So that actually enhanced our understanding significantly. So basically, with this graph, what I want to convey you is that if we consider origin of our planet at around 4.5 billion years, what we see is that in case of Earth, we have evidences present on the surface for a very recent time, less than actually a few hundred of million years. And the initial processes like impact cratering, volcanism, and tectonics, these processes, if we want to study how these processes were influencing in initial time of evolution of planet, actually what we need to look is the Moon and Mercury and Mars, because these are the bodies which actually has information saved or preserved on the surface for very initial time. So this information is actually based on the age of planet or crater through this what we get through crater counting. Then, very surprisingly, before space missions to Venus, our understanding was that Venus is actually twin planet of Earth. But with space missions, we could understand that a recent resurfacing event happened in case of Venus, because we do not have any evidences of early system of Venus evolution. on the surface. So this was a interesting outcome of planetary exploration, because before planetary exploration our understanding was that physical properties and as well as the surface evolution of Venus is very similar to Earth. So this is how comparative planetology actually enhance our knowledge when we start putting different processes on a single graph. So as a first step, what we want to know is that if basically every planet receives some amount of light from sun, and how basically it actually reflects. So the first thing in very initial time in all initial missions, what we did was we actually aimed for having radiance of all these LS bodies. Here just few of them are listed for example, and you can see that the x-axis is wavelength and the y-axis is spectral radiance, and each body actually reflects light in a different way, and that actually uh, tells first order of information of its surface composition. So the radiance is composed of surface reflection, of solar irradiance, and radiance coming from planetary body in the mid and thermal infrared range. So the radiance can be actually divided into two. One part is dominated by reflectance, and another part is dominated by the emission. So both the ranges are very important to study, and when we combine, we actually can get the overall response from the planetary body. So these were some of the initial measurements which could actually give us information about albedo of planet as well as the temperature of planetary temperature of the surface of planetary body. So if we just summarize all planetary missions, anyway it's not possible to put it in one slide. Some of them I have mentioned with main focus on our inner planetary bodies. So you can see that each of our solar system planets are now visited by some or other spacecraft, either orbiter or flyby, lander or rover, and that actually by combining information from each of this planet actually tells us about the overall solar system evolution. Some of this we will discuss in detail in subsequent slides. So basically, our approach is that we need remote sensing observation. We also need in situ information so that we can actually interpret our remote sensing observations. We also look for terrestrial analog sites. Just so we, in case of Moon and Mars studies, we try to go to areas where uh, we may expect this kind of environment, and we actually look for the processes just to understand that what kind of processes may actually dominate on other planetary bodies. And then we have natural samples, meteorites. So basically, when we combine all these four blocks, what we get is our puzzle solved. So though it's not that simple, but this is in general approach what we actually opt for. So now my major concentration now is on remote sensing. So out of these four blocks, what I showed before, the main concentration is on remote sensing, analysis. So remote sensing, basically, here I'm just showing the wavelength range from ultraviolet to infrared, and you can even go further. You can go up to gamma rays, and you can you can also have radar measurements. So you select your instruments based on your scientific objectives. So in general, these are the measurements which I have listed here: reflectance spectroscopy, gamma ray spectroscopy, radar measurements, and X-ray fluorescence spectroscopy. These are the measurements which actually give us information about surface chemical composition, which is very important to understand the overall planetary body evolution. And the main advantage of having remote sensing observation is that we get global coverage. So if we go with lander or rover, those are in situ observations, which are very important to understand remote sensing observations. But those are site specific, which can be actually utilized to have the global coverage and to have the global understanding using remote sensing observations. So basically, this kind of global coverage help us to identify resources, map the surface, and by matching mineral fingerprints, because each mineral actually, as I said already, forms at a specific temperature and pressure. Actually, that tells us about the initial conditions, initial forming conditions of a planet. So selection of wavelength is dependent on your scientific objectives. Suppose if you want to study atmosphere, UV part is actually uh, is important to study. If you want to do surface, if you want to study surface mineralogy, one can concentrate on near infrared wavelength range, spectroimaging in visible wavelength range, and if you are focusing on bulk composition, one can go for X and gamma ray spectrometers. But in general, most of the satellite missions go with a suite of instrument, which most of the time includes all these observations. So one can combine observations from radio waves up to gamma ray to actually understand morphology, mineralogy, and bulk composition of a planetary body. So basically, I will just very briefly, I will talk about that what we measure or what we detect through remote sensing observation, because this will be covered in detail in next webinar. So basically, what we are interested is to understand is interaction between sunlight with the surface. So this incoming energy from sun actually interact with the planetary body. Mainly right now we are focusing on airless bodies, and some part of this is reflected from the surface, and if there is thin atmosphere, through atmosphere, some part is absorbed uh, and heat the surface, which then is emitted in longer wavelengths, and from all the directions. So basically, it is important to have a good understanding of electromagnetic radiation interaction with the surface, uh, in order to interpret our remote sensing observations. So what kind of tools we can use? One of the main important tool is spectrometer. which can operate in several different wavelength ranges. Here I have just shown you a graph for near infrared wavelength range from 0. Visible to near infrared zero point 0.4 to 2.5 micrometer. And what you can see is there are some diagnostic absorption features which actually tells us about primary interaction with transition metals, in this case with iron. And this kind of reflectance spectrum actually help us to understand chemical and mineralogical uh, um, uh, characteristic of a planet. So in this particular, in the near infrared wavelength range, the main dominating processes which actually causes absorption are electronic processes, and that is high energy photons absorbed by electrons, and these energy states or the wavelength is controlled by the atom and the crystal structure. And so basically to interpret this kind of reflectance spectra, you have to have good understanding of how and in which particular crystal structure this transition metals are sitting, which actually describe the absorption. So the advantage of this kind of spectroscopic observation is that these are having high spectral resolution and simultaneous measurements. But the disadvantage is that the signal processing of this kind of instruments are complex and interpretation is quite tricky because you need some kind of in situ information. And you need also a very good understanding of other processes which can actually influence these absorption bands. Another tool, if we talk about, is very simple, and every spacecraft is having it. Is cameras. So observation in visible wavelength range, and this is a example taken from our recent Chandrayaan 2 mission to moon, and this is a TMC2 3D map of a crater which actually shows the depth and diameter relation of this crater, as well as it also gives us some information of physical properties of particle size and surface roughness. So basically, observation in visible are kind of a qualitative data. It gives a high resolution three-dimensional topographic maps. This can be used for albedo measurement, although not quantitative. And this albedo, which is actually dependent on composition, size of particles, and surface roughness. So this kind of simple tools are actually very important to understand, to have the first cut information about the surface. So basically, because we are mainly focusing on surface composition, why to study surface composition? So basically, to understand geological history of the planet, and this would constrain the thermal evolution of the planet. So just to understand the overall evolution process, we actually, because we can't go in too deep, even in case of earth we have not yet managed to go up to mental. So what we rely on is actually on the surface information, but we know that what comes on surface is actually due to the internal processes, and that basically actually are indicator of the thermal evolution of the planet. So it's very important to study surface composition. Then basically our main focus is on how much iron is there on surface, because this is, first of all, the reason is that it can be comparatively easy to detect, because iron oxide has its signature absorption bands in wavelength range between in this near infrared wavelength range, and these spectrometers are, if you consider thermal part, these spectrometers are actually comparatively easy to operate. And so, and this actually provide constraint on planetary evolution models. And then we are also interested in studying how much space weathering has occurred on planetary surfaces, and that would constrain the space environment of planet over its history. So basically, because we are in, our main interest is to understand the evolution of the planetary body, it's very important to constrain the space environment of the planet over its history. And thus any of the material in the exosphere come from the surface. So this would constrain the interaction between exosphere and magnetic field, solar wind, and or surface. So it's very important to understand the surface uh, exosphere or surface atmosphere interaction processes to understand the overall evolution of a planetary body. And these are the main reasons why we want to study surface composition. So I will just like only very briefly, I will go to all inner planetary bodies one by one. Mainly this moon will be covered in detail in the third talk of this webinar series. So just to for completeness, I have included here moon, and that actually shows hemispherical asymmetry, and this was not known before having a orbiter mission to moon, because only the near side of moon is actually facing towards earth. So through telescopic observation, we could only see this kind of features. And uh, at that time our understanding was that the far side of the moon, or the other side of the moon, would be similar to this. But when we got our first pictures, we actually realized that that is not the case. So there is hemispherical asymmetry between near side and far side of the moon. And the general observation is that it's a heavily cratered surface, and partly filled by lava flow. So if you consider overall, moon is dominant by highlands of about 83%, and mare regions are mainly confined in near side, which actually which is basically 17% of the overall surface. So there is dichotomy which has to be again understood in detail. Then we start with Mercury. So here I have just listed few of the basic characteristics of this planet. This is the smallest planet in our solar system, almost 60% smaller than Earth, and it is comparable to our satellite moon in size. But very interestingly, it's the second highest density, second highest dense planet of our solar system, just little less than our own Earth. So why it is so? Why it is so dense? We have to understand that. And for that again we need missions. This planetary body do not have any satellites. it has a magnetic field, dipole type, very similar to what we have in case of Earth, but with a very, very almost 1 by 1,000 times of Earth. So the strength of that magnetic field is very low, but still it has a magnetic field, which was again a surprise because initially it was thought that Mercury is similar to Moon and Moon do not have magnetic field, and it was expected that probably Mercury would also not have a magnetic field. So basically, this Mercury was expected to be similar, thought to be similar to Moon, with bright craters and dark plains. But then now we know that actually these two planetary bodies are very, very different, and there are no evidences of plate tectonics. What you see here is actually false color image. It's an enhanced color image, which actually gives a much better idea of features in comparison to this albedo image. So one of the very interesting outcome of Mercury exploration was that because it's very close to Sun, it was not expected that we will have volatile concentrations on the Mercury, but our our orbiter missions actually provided us information that there are certain regions where if you look to temperature, it goes really down. It's about 150 to 200 Kelvin. So this is the north pole of Mercury, and then there are certain regions which are actually permanently shadowed. Which are never ever seeing sunlight for since a very, very long time, since a few billions of years, and these are actually significantly larger than at the moon's pole. So this was another surprise what we got, that the size of these PSRs are actually large compared to moon, and there is and it is expected that these areas may have volatile concentration, just similar to what we are seeing in case of moon. So this was a kind of a very surprising result from Mercury. I'm not listing all main important results. I'm just glancing through few of them because of limited time. So next planetary body is Mars. Okay, I could put Venus first, but so Mars is a water planet. So now we know that at a certain point of Martian history, actually it had liquid water flowing on the surface, but now the condition of Mars do not support it. So basically the surface gravity is 0.38 of Earth, mass is zero point 0.1 of Earth, mean density is less than Earth, and the diameter is actually is half of Earth. So it's about half of the Earth size. It has two satellites, Phobos and Deimos. These are probably the captured satellites, and it has remnant magnetization of surface rocks, very similar to what we see in case of moon. It has thin atmosphere, which is actually dominant by 95% of carbon dioxide and 3% of nitrogen. Whereas in case of Earth, we have 79% of nitrogen and 21% of oxygen. Mars is also having polar caps, very similar to what we have in case of Earth, where these polar caps are actually covered by by water and carbon dioxide ices and frost. Which actually, and now with many rover and lander missions to moon, to Mars, actually we know that there are evidences of running water in early history of Mars. This is also home of highest volcano of our solar system. So you can see this these sets of volcanoes here. These are very very huge volcanoes. These are the highest in our solar system, and that is again very interesting that in such a small body in comparison to Earth, how it could actually sustain such high volcanoes. So and then on top of that it shows dichotomy. As you can see, some are very smooth areas, whereas some are very very cratered areas in this topographic map. So again this kind of dichotomy exists, which is required to be studied in detail. Some people actually hypothesize that these plain areas could be actually ocean in early history of Mars, or some kind of resurfacing event happened, and the cratered surface probably is actually the old surface, the oldest surface of Mars. So in case of Mars, we because we are always curious, and Mars was actually initially thought as the best possible place to find mm, even life. So after Moon, this is the second most visited body by orbiters and landing spacecrafts. First successful satellite mission was in 1971 by USA Mariner, and 1976 was the first lander on the surface of any another planet. So it's a very interesting planetary body, and presently we have six orbiters surveying the planets, and out of this, one is actually from India, Mars Orbiter mission, accompanied by Mars Odyssey, Mars Express, MRO, and Maven. Each of this actually orbiting Mars with a specific scientific objective. For example, Maven is mainly concentrating on studying the atmosphere of Mars. So you can see here, this is mom, and these are like some of the landers. This is one lander, and here is a rover of almost a car size of rover exploring the surface of Mars. So we have several missions, and with those missions starting from 1970s, we have now a good understanding of how this planetary body evolved, but still a lot of things, many open questions are there, which has to be again addressed through future missions. Some of the major points I have just listed here. Curiosity finds evidence of persistent liquid water in the past. So basically, first time we could have a sample which was studied by this Curiosity, and it found that rivers and lakes persisted in the scale crater where it landed for perhaps a million years or longer. Another interesting finding is that MRO and Mars Odyssey actually mapped water ice, because if we plan future missions to Mars future, suppose if we are planning manned missions to Mars, we actually need access to water not too deep. So basically, this square area shows the area where one can actually land, and water is accessible beneath the surface, as little as inch below the surface. So this could be a very good place to land. And then some of this water rich minerals found, and this one is actually a site. This is the Jajiro crater, where probably the the next Mars mission will lead to again basically study in detail the possibility of I mean to have evidences of some form of life on Mars. Then comes next is Venus, our twin sister. So if you compare physical parameters, what we see is that its mass, density, and radius and its gravity is actually very much comparable to Earth. And based on these observations, initially it was thought that Venus is similar to Earth. But then with our orbiter missions we understood that is not the case, and Venus is actually very different than our own planet. It has slow rotation, so the it takes about 225 days to rotate in on its own axis, and it has retrograde movement, so all planets actually moves in one direction, and Venus is opposite to that, so it's in clockwise direction, whereas all other planets are actually moving in anti-clock direction. The atmospheric pressure is very different than Earth. It is about 90 bar, and the temperature is respective to equatorial or polar region. It's always 450 degrees centigrade. So it's the hottest planet of our solar system. It do not have continent ocean dichotomy as we have on Earth, and no plate tectonics is observed, which was again initially was an assumption. The crater density is much lower in comparison to Moon and Mercury. So some kind of global resurfacing probably happened before 500 million years. And the atmosphere of Venus is 95.5% carbon dioxide and 3.5 percentage of nitrogen. So it's not at all a hostile environment. You can see here in topography some so this is like a body with many volcanic features is the all I mean the surface features are actually dominated by volcanic features. And again this gives us a very interesting platform to understand that Earth would probably like what kind of path Earth would take in future. Either it would move towards Venus, or it would move towards Mars kind of geology. So exploration of Venus started very early in 1962. Mariner 2 from USA, that was the first successful mission to Venus, which actually confirmed very hot surface environment. Venera 4 from USSR was the first successful entry to atmosphere, and that detected CO2 with mixture of nitrogen. Venera 9 was the first provided the first geochemical analysis of the surface material, and TV panoramas like one shown here was taken by Venera 9, 10, 13, and 14. All these missions actually survived for a very short time on the surface because of its very high temperature and not so comfortable environment. Presently, we have one mission Akatsuki, which is mainly focusing on studying Venus atmosphere operational. And India is also planning next mission to Venus in near future. This is a simplified geological map of Venus. What we actually created using the radar observations. So what you can see here is basically the I mean it has volcanic units and rifts and tectonic components, terrains, and impact craters. So basically, it's what we have so far is actually the understanding of Venus surface is actually based on basically the landing missions and recent this Venus Express mission. So this is the current state of the understanding of Venus surface. So basically, I tried to cover all this the information of I mean what is the current state of I mean obviously I have not covered all the major findings of surface related studies, but I just try to focus on few of them. And basically if you want to when want to have more details, you can actually look to some of these books which are actually really good and give us the basic information of these planetary bodies. And at the end I would like to acknowledge matter as well as pictures in this presentation has been taken from various books, journals, and websites. I'm grateful to the authors and contributors of these sources and materials. Thanks.